We walk on it every day, we build our homes on it, we plant our food in it, but how often do we stop and think about what lies beneath the surface of our planet? Just like a good book, Earth has layers full of stories. These layers hold clues to the planet's fiery birth, its ever-changing landscape, and the very air we breathe. Our journey takes us on an expedition to the center of the Earth, a place of immense pressure, unimaginable heat, and astonishing beauty. We'll venture through the rocky crust, dive into the churning mantle, and explore the molten metal core. Along the way, we'll uncover the forces that drive earthquakes and volcanoes, and the invisible shield that protects us from harmful radiation. Join us as we delve deep, peel back Earth's layers, and uncover the secrets hidden within. Our journey begins with the Earth's crust, the solid outermost layer that forms the ground beneath our feet. It might feel incredibly vast and enduring, but compared to the rest of the Earth, the crust is surprisingly thin. Imagine an apple. The skin of the apple is akin to the Earth's crust in proportion to the entire planet. The crust is composed of a variety of rocks, minerals, and soil. It's not uniform either. We find two distinct types, oceanic crust and continental crust. The oceanic crust, as its name suggests, lies beneath the oceans. It's denser and thinner, primarily made up of dark, heavy rocks like basalt. Continental crust, on the other hand, forms the land masses we inhabit. It's thicker and less dense than oceanic crust, composed of lighter-colored rocks like granite. The differences in density between these two types of crust play a crucial role in the dynamic processes that shape our planet's surface, as we'll see later. As we descend further, we leave the solid, familiar crust behind and enter the Earth's mantle. This is where things start to heat up, literally. The mantle is a thick layer of hot, dense rock that makes up a whopping 84% of Earth's total volume. It's about 2,900 kilometers, or 1,802 miles thick, a stark contrast to the thin crust we just left behind. But it's not just the heat that's remarkable. The mantle behaves in a fascinating way. While it's primarily composed of solid rock, the immense pressure and heat cause the mantle to act like a very viscous fluid over geological timescales. Imagine a lava lamp, the blobs of wax slowly rising and falling. That's similar to what's happening in the mantle, a process called mantle convection. Hotter material from deep within the Earth rises towards the surface, while cooler material sinks back down. This continuous cycle of heat transfer is a powerful engine that drives the movement of tectonic plates, a key player in shaping continents, causing earthquakes and triggering volcanic eruptions. Our journey now takes us to the Earth's outer core, a place of extreme conditions and a dramatic shift in composition. Gone is the solid, albeit slowly flowing, rock of the mantle. Here, we encounter a swirling ocean of liquid metal. Imagine a sphere of molten iron and nickel, twice the size of the moon, churning constantly. That's the Earth's outer core. The temperature here is staggering, ranging from 4,500 degrees Celsius to 5,500 degrees Celsius, or 8,132 degrees Fahrenheit to 9,932 degrees Fahrenheit, hotter than the surface of the sun. The intense heat keeps the metals in a liquid state, and this liquid metal is in constant motion. But it's not just heat that makes the outer core special. The Earth's rotation, coupled with the movement of the liquid metal in the outer core, generates electric currents. This, in turn, creates a magnetic field that surrounds our planet. This magnetic field, also known as the magnetosphere, acts like a giant shield, deflecting harmful solar wind and radiation from the sun, making life on Earth possible. Finally, we reach our destination, the Earth's inner core. If the outer core was extreme, the inner core takes things to another level. Here at the very center of our planet lies a solid ball of iron and nickel, about 1,220 kilometers thick, which is roughly 758 miles. You might think that with temperatures estimated to be around 5,200 degrees Celsius or 9,392 degrees Fahrenheit, the inner core would be liquid. But the pressure here is immense, over 3.6 million times the pressure at sea level. This colossal pressure overwhelms the effects of the high temperature, forcing the iron and nickel atoms to lock into a solid, incredibly dense state. The inner core isn't just a static ball of metal, it spins, and it spins slightly faster than the rest of the planet. The heat radiating from the inner core, generated from the radioactive decay of elements like uranium and thorium, drives the convection currents in the outer core, which in turn powers Earth's magnetic field.